Welcome to a SimCenter AimSim Student Edition tutorial covering a problem of machine dynamics and vibrations. The problem statement is that a loaded trailer with a mass of 1,000 kilograms rests on two wheels. Evaluate the behavior of the system if the suspension cannot compress further than 5 centimeters. Also, how do additions to the suspension and of wheels affect the behavior of the model? With the goals for the tutorials being building models within the mechanical library, performing studies to evaluate the vibrations of the system, and how to utilize simulation data to create the equations of motion for the system. This video will be broken down into 4 parts, with this being part 2, determining how does the model behave with both a critical and a realistic damping value, and what are the equations of motion with these new damping values. For a critical damping value, the damping ratio for the system is 1, and the damping value is equal to the critical damping value. The critical damping for the system can be found with the equation shown, using the mass of the trailer and the angular frequency found in the previous video, of 19.8 radians per second, finding that the critical damping value is 39,600 newton seconds per meter. The equation of motion can be established with this damping, mass, and stiffness values, which can be solved to find the time response equation, which can be compared to the model's motion within AimSim. The critical damping can also be found within AimSim, beginning with the same model and parameters that were created at the end of part 1. Open the Global Parameters menu and create a new real parameter with the name damp that will serve as the damping value of the total system. The parameter's initial value can be set to 10,000 as a placeholder for now. Within the spring and damper components of the model, change their damping value to half of this global parameter created. And from here, run a batch sweep of this global parameter within the study manager. The study definition will be varying between two limits. The step size can be 5,000 with the number below as 0 and number above as 10. Moving to the Simulation tab, run the batch run from the Study Manager window. With the simulation complete, open the results plot for the mass displacement and edit it to display the results for every batch run. A critically damped system will approach the equilibrium in the fastest way possible without any oscillations. Zooming in shows the light and dark gray lines converging on this point, but the dark one never dips below the equilibrium position, making it the most accurate value for critical damping. This result set is associated with a value of 40,000 newton seconds per meter, which is very close to the calculated value, verifying the initial results. With the critical damping value confirmed, the damping global parameter can be adjusted to it. The motion of the mass can also be compared to the time response equation calculated using the same clock source and function block as in part 1 with the equation entered. Before performing a simulation, be sure that the linear analysis option is enabled. For linearization times, leaving the only value of 0 is okay. After running one simulation, within the linear analysis menu, open the eigenvalues. Here, the resonance frequency is present and a damping ratio that is very close to 1, showing a critically damped system. Opening the plots for mass displacement and function output are shown to be equal as well. Through research, a realistic damping ratio for a trailer suspension is found to be 0.2. With this and the critical damping value, a realistic damping value can be found to be 7,920 newton seconds per meter. Inserting this damping value creates a new equation of motion and in turn a new time response equation as well. Changing the global parameter once again to reflect this realistic value and inserting the new time response equation into the function block. Perform another simulation with linear analysis, and once complete, evaluate the eigenvalues menu, where there is still the same frequency and a damping ratio that is approximately 0.2. The mass displacement, or output from the function block, will also show the trailer's behavior when being placed onto a realistic suspension, initially uncompressed. And with this concludes part 2 of the demonstration. Thank you.